Welcome to Structural Analysis 2 video series, unit number 4, stiffness method. Lecture outline: numerical on rigid frame. Numerical problem as follows: analyze the rigid jointed plane frame supported and loaded as shown in figure by stiffness method. Draw bending moment diagram. In the given figure, a rigid jointed frame is given. AB column of a 4 meter is loaded with the 32 kN point load at the midspan. Length of AB is 4 meter and moment of inertia is 2I. Beam BC loaded with the 48 kN point load at the midspan. Length of BC is 3 meter, moment of inertia is I. Column CD loaded, there is no any load on column CD. Moment of inertia is 2I and length of column CD is 4 meter. At C there is a roller support which not allow the horizontal translation, so it become non-sway frame. At A and D there are fixed support. So first step in the solution, first find out degree of kinematic indeterminacy, DKI, or degree of freedom. Now there will be rotation at B and at C. So 2 degree of freedom will be there, theta B and theta C. No translation, so delta will not be there and it become a non-sway frame. Second point, assign the coordinate direction to the unknown displacement. Now the unknown displacement are theta B and theta C. So the let assume they are in an anticlockwise direction, positive. Let call them D1 is equal to theta B anticlockwise and D2 is equal to theta C anticlockwise. Both are positive in a sense. External force or moment acting in a coordinate direction ADL. Our coordinate directions are theta B and theta C. There are no any external moment acting along theta B and theta C. So AD1 and AD2 is equal to 0. Next point, force in the coordinate direction of a restraint structure ADL. Make a member restrain and find out the friction moment at each end. First column is A B column, and at A there is a friction moment MFAB for a point load of 32 kilonewton. The formula is WL by 8, 32 into 4, length of column is 4, divided by 8, it becomes 16 kilonewton meter. So it will be a 16, make it correct, it is a 16. So friction moment for AB column is 16 kilonewton meter at A and at B. Now the friction moment for beam BC, load is 48, formula is WL by 8, 48 into length of this BC is 3 divided by 8, it becomes 18 kilonewton meter. So it is not 16, it is 18 kilonewton meter for end B and C. So these are the friction moment at B and C. And for column CD, there is no any load, so friction moment will not be there, value become 0. Now ADL1 means the forces in the coordinate direction 1. So this one is our location of coordinate 1 and here is our location of coordinate 2. So at coordinate 1 there are two moments, one is 16 kilonewton meter for BA and one is 18 kilonewton meter for BC. So it become minus 16 plus 18 become 2 kilonewton meter, net moment become 2. And for C, for CB there is 18 kilonewton minus, which is a clockwise sense, minus 18, and 0 is there for CD. So only minus 18 will be there. So net moment will be minus 18. So at 1 and 2 coordinate location, the net moment will be 2 and minus 18. Next point is determine the stiffness matrix S formed by forces in the restraint structure subjected to unit value of D1 corresponding to unknown displacement. Now let consider d1 is equal to theta b is equal to unit rotation in the direction of theta b. So this is our B point, and keeping the far end fixed, A and C are the far end, which is let keep fixed, and allow the unit rotation at B. So by applying unit rotation at B, so both member will get rotate, and the rotation will be 4 EI by L plus 4 EI by L. So both member will rotate with the magnitude of 4 EI by L. Now the length of AB is 4 and moment of inertia is 2I. So 4E into 2I divided by 4 plus length of BC will be a 3 meter and moment of inertia will be I. So 4EI divided by 3. So it becomes 3.33 EI. Now this is at coordinate location 1. So if this one is a coordinate location 1 and at C there is a coordinate location 2. When we apply the unit rotation for coordinate 1, what happen at 1 that we will get in term of S11, and there is unit rotation for 1. So what happen at 2 we will get in term of S21. Now at B both members rotate, so we adding them and we find out 3.33 EI. Now at C half moment will carry, so it become 2 EI by L CB, and it will be in the same sense in a anti-clockwise sense. Here it is in a anti-clockwise sense. So far end also it having the same sense, which is a anti-clockwise sense. So positive 2 EI by L, and it become S21. So 2 EI by L, length of CB is 3 and moment of inertia is I, so it become 0.67 EI. So we having, by doing unit rotation theta b is equal to 1, we having a first column of stiffness matrix S11 and S21 values. Now to get the second column of a matrix, apply the unit rotation at theta c in an anti-clockwise direction as a positive. So at C let apply the unit rotation theta c as 1, and by keeping the far end fixed, so far end is B and far end is D. So this column beam will get rotate in a downward direction and in an anti-clockwise sense, and column will get rotate in a anti-clockwise sense. So both member will rotate at C, and that rotation we know that it will create the moment due to the unit rotation theta c is equal to 1. It will create the moment which is 4 EI by L for BC and for CD. So putting the property of that members 4 EI by 3 is the length of beam BC plus 4E into 2I is the moment of inertia of column CD divided by length of column CD is 4. It becomes 3.33 EI. Now for far end, where is our coordinate 1? Now this one is the location of coordinate 1. This is the location of coordinate 2. And we are applying unit rotation for second coordinate in the direction of second coordinate. So write down that letter after 1, after the position of 1 and 2 coordinate. So we having the S22 value. Now find out value for S12, and that will be half, that become 2 EI by L in a, again in a anti-clockwise direction. Same moment will be carry. So 2 EI by L, putting the value of I for the beam BC is I, length is 3, so it become 0.67 EI. So we having now the second column of stiffness matrix. Okay, so remaining part will be resumed in the next video. Okay, thank you.